see it? Okay.
Awesome.
Is that Lee Won? Where is Lee Won? Lee Won's not here.
Admit.
Admit, everyone admit.
Kings Park.
Admit all.
Oh, I think you
Hello.
probably later just cancel the need to admit people and just make it that just people are automatically admitted.
Yeah, how do I do that?
Wait, why do Kings Park have this meeting room?
Because it was dispersed for everyone in case someone has to
Oh,
vote.
Hi.
okay, wait.
Hello, Lee Won.
Hi.
Hi. Can we test out your ability to share?
Yeah. I need to send a request.
Yep.
We're hearing.
So only 4 of us in this Zoom, or some other
Give me
people?
1 second. I think the sound is coming through, not where it should be coming
See it?
from.
Okay. Awesome.
Is it always 702?
Um,
Is it always gonna be 702? Not 701, right?
In case you're worried about the small number of people, I think there are people in place in the room.
Okay. But can I see them? Because how do I know they have some questions or like
I think they're trying to get that set up. I'm not sure. I'm not in the room. I was hoping to be there, but I got stuck on something.
okay.
Hi guys, trying to figure out the sound. Give us a moment.
The speaker would also like to see the room.
Yeah, I hope I can see the room. Of course.
No, I'm very sympathetic to this. I know what it's like to teach when everybody's got their video turned off.
Okay, I think it's good to go. You can try sharing your screen now.
Okay. Yeah.
Wait, we don't have the camera open, right?
That's right, but
Okay.
I think that's too late for now. Like I think maybe in the future just use the room.
How do I- Just do the, I'll try that.
This is linked to the parts.
I know. I'm asking you for the next few seconds, like it's something that's like you're allowed in my fear. Because it would be the. If he's something. Yeah.
Okay, hello everyone. Welcome to the inaugural quantum theory seminar for the semester. I'm excited to be having Liuan Chen from Harvard talking to us today about his work called Toward a Practical Topological Quantum Computer. Liuan is a PhD candidate in applied mathematics at Harvard, advised by Professor Arthur Jaffa. His work spans topological quantum computation, quantum error correction, and quantum simulation. Recent results establish conditions under which analog quantum simulators with only global control are universal. And with that, Leon, take it away.
Okay, so hello everyone, can you hear me? Yeah. So yeah, if you have any question, please like just interrupt me and then yeah, just ask. So I am Li Yuan, I am from Harvard, and today I will talk about our recent work based on these two work about how to construct a practical topological quantum computer. Yeah, and the outline of the talk, I will give a brief introduction of the background, and then I will talk about the specific non-abelian code called quantum double model S3 and how to realize universal quantum computation in this system. Then I will talk about how to realize it on current quantum devices, and then how to do active error correction in this system. Finally, I will give a summary and outlook of this work. So before I get started, let me thank all of my collaborators. So the first work shows how to realize universal quantum computation. And actually, I collaborate with Yuanjie, Ruihua, and Arthur. Yuanjie is a PhD at MIT, and Ruihua is a postdoc at Berkeley. And Arthur is my advisor, of course. And for this error correction in progress, I work with Siyuan. Now he's a PhD student at Harvard. So these are the two works. Okay, so let me give a one-page introduction about why people will be interested in quantum error correction. Because if we want to do quantum computation, and we know that noise is everywhere, so we need to do error correction to make the computation robust enough. And then to do that, people actually invented many different error correcting codes. One of the example is this one, this Tori code and surface code. I believe many of us know about the construction of that. Basically, you use a two-dimensional array of qubits, physical qubits, to encode one logical qubit. And then you can detect error and pair up the errors and then to correct all of the errors, like if the error rate is low enough. So this can make it become robust. But other than just doing error correction, we need to do universal quantum computation. Namely, we want to realize any unitary gates in the circuit we want by some specific small universal gate set. These are just a single qubit or 2 qubit gates that can simulate any large unitary we want. So a typical gate set is called Clifford plus magic gate. And in surface code, actually we can have fault-tolerant Clifford gates. For example, in this picture, I use a representation of this surface code. This is 2-dimension. It encodes a logical qubit 0 and 1. You have some checks, and then the logical operation is this large X string or Z string go across the whole copy. But in surface code, we do not have this fault-tolerant T gate. So we need to do magic state distillation. This is a very famous work by Kilera and by Harvard. They do distillation in experiments. And magic state distillation is like you have many noisy T states, and then you do like maybe 5-to-1, 15-to-1 distillation to prepare a T state with higher fidelity. So because we do not have a fault-tolerant T gate, we need to ensure our T state or T gate has very high fidelity, like 10⁻⁻15, by doing many rounds of distillation. And this will still make the computation reliable. Okay, so you can see there is a compatibility problem. Like when we do error correction, yes, we can have some reliability in the code, but we cannot do universal quantum computation. And if you have a single atom, you can do universal quantum computation, but the problem is that it is not fault tolerant. This compatibility problem actually arises everywhere in quantum computation. Namely, you have one property, you cannot have another property very perfectly. So there are some resource analysis papers about how to use surface code to realize Shor's algorithm. If we want to use Shor's algorithm to operate in 1 day, you need 1 million qubits, and 90% of them are from magic state distillation. So actually, magic state distillation is very resourceful. And there are some other proposals like 3D color code or code switching to overcome this problem. But the problem is that they also introduce some extra overhead, and some resource analysis paper shows that they also cannot how do I say, compete with this surface code plus magic state isolation protocol. So the question is that, do we have any like two-dimensional code? We do not have extra dimension like 3D color code. And then we also do not have magic state isolation. This code directly have a fault-tolerant universal gate set such that we can use this single code to realize fault-tolerant universal quantum computation. And yes, Kitaev says, in many years ago, he says, yes, it is possible. In his seminal paper, this fault-tolerant quantum computation by Anians. He said it's possible because surface code is DZ2, the quantum double of Z2 group. So to be clear, Z2 just means qubits. A qubit has two states, so you have a Z2. And E and M particles, they are the quantum double built upon this Z2. So they have like this kind of Z2 fusion rule. And he says in this paper, you can have a non-abelian group G, and you construct a quantum double model based on this non-abelian group G. You may possibly have a fault-tolerant universal quantum computation in 2 dimensions. So here, we mean non-abelian group G means that we have a group qubit of dimension G at each edge. And then this DG is constructed by taking the quantum double of this G. So it's like a higher level surface code. But in his construction, the G he takes is A5. This is like a permutation, not permutation, like some symmetric permutation of 5 elements. It has group order 120. So it requires a 120 dimensional qubits on each edge. And it is impossible to be realized in current quantum devices. So even though he proposed this idea and he somehow opens the field of topological quantum computation, but actually the realization is still very hard because we cannot find such material or such realization having this kind of solving this difficulty. So the question is that, can we find a very experimentally friendly code can do this kind of universal fault-tolerant quantum computation in 2 dimensions? Okay, and the answer is possible. And this is what we have done in our work. So this is surface code plus magic state isolation. And we try to find a minimum setup. It's a non-abelian topological code. Directly realize a fault-tolerant universal gate set. And our solution is this quantum double model of S3 group. Yeah, so let me explain this picture. This picture is like, we still have some stabilizer measurements, or maybe I call it as anion type measurement. And there are 8 types of anion in this system, labeled by A to H. And this system is constructed based on a 2-dimensional array of qubits and qubits, because S3 can be decomposed into qubit and qubit, as I will explain later. In this single code, our result is that if you have a good decoder, you can have a fault-tolerant universal gate set in 2 dimensions. Okay, so why we select this S3 as our solution? Yeah, because they have many different advantages. The first one is S3 is very experimentally friendly. Because this S3 group order 6, so you only need like 6-dimensional local Hilbert space to realize this code. And this semi-direct product structure in the S3 group can decompose this Hilbert space into qubit and qubit. And you can also show that they only use simple circuits to realize those manipulation of anions. So it is really experimental friendly. And there are many papers like before shows that, okay, how can you realize non-abelian topological orders using circuits? And I believe like Professor Kim also have some like realization in this, in this direction. Also, it has computational power, very powerful. People have shown that you can realize universal quantum computation by braiding and measurement. So the original proposal was from Mushong, and then Cui and his collaborators like enhance this to another encoding. I will explain later. Also, they can enable error correction, and they have some partial error threshold in certain conditions. So it seems that S3 quantum double has many good properties. But as I said before, when you have this kind of properties, you investigate that in one direction. If you put all of these 3 together, you may face some compatibility problem. And in this paper, what we want to solve is this compatibility problem. We want to put all of these three together.
Everything's
Come on.
gonna break down in 15.
Sorry? Sorry? Okay, so we try to combine all of them together and get a concrete like framework for building a topological quantum computer. So is that clear? If it is clear, I go to the some details about this construction. Okay, so it seems there is no question. So I will just give a brief introduction about how topological quantum computation works. Like in Kitayu's paper, he actually proposed that topological codes have some intrinsic robustness. And the mysteries of that is from the anyons. So let me explain this using surface code. This is surface code. We have some X checks, Z checks, and also these logical operators. And its ground state, namely no error in this system, encode a logical qubit 0 and 1. So when you have some error, I say anyons are created in pairs independently IID with probability P. So this is the case. In this two-dimensional system, the X error happens somewhere, the Z error happens somewhere, and also this XXX error happens somewhere. So this X error will be detected by these Z stabilizers because they anti-commute. So you have a -1 result. And also these Z errors will be detected by this X stabilizer. You also have some -1 result. So people from condensed matter will say this X error will create a pair of M anion magnetic flux. And this Z error creates a pair of E anions, the electric charge. So the error correction procedure is like we want to fuse those anions because those anions are always created by pairs by the design of this code. So we just apply some, after the decoding, we guess, okay, how this error happened, and we apply some correction operation like the X operator to cancel this error, or this Z operator cancel the error, or this X operator. So this is also equivalent to we bring those anions together. We fuse them by pair, like moving this M anion to another M anion and fuse them together, and also fuse these two anions together to correct those errors. So as long as the correction and the error does not form a homologically non-trivial loop, your correction works. You do not have logical error. But here, this is the case. We have a very long X error. And then our correction will tell us, you should move the anion to the boundary. This is bad, because this actually introduces a logical X operation. So you have a logical error. So the goal of error correction is that we want to do, like we want to guess how error happened, and we want to ensure that our correction does not introduce any logical error. So there is a concept called threshold PC, sorry. When the error rate is below this threshold PC, and you have some code distance as the system size, your logical error rate can be suppressed exponentially by this P over PC to this power. So this is the goal of error correction, and such that we can always increase the system size. And it gets larger and larger. Our logical error rate gets smaller and smaller, so it becomes reliable to do computation. This picture can be generalized to non-abelian codes. In non-abelian codes, we have non-abelian anions. So they are somehow different, because previously those E and M particles, they are abelian anions, but right now we have non-abelian anions. Non-abelian anions have two key distinctions. The first one is called degenerate fusion outcomes. Like if I create a pair of alpha anion, a pair of beta anion, if the anions from different pairs are fused together, they can have different possible results. And this is a quantum superposition of those potential results. So you need to do a measurement to make it become like clear which anion you get. This is one like result. And also another one is just braiding. You have a very strange braiding phase when you exchange the two particles in 2 dimensions. This is unlike the +1 or -1 phase of boson and fermions. Okay, so these are two distinctions. So these two characteristics bring us some new thing. The complicated fusion and braiding structure can give us more computational power. but it can also give you some difficulty in encoding and decoding of this code. So the point is that how can you like solve those problems in this kind of very complicated problem? So let me introduce how to do encoding use this non-abelian code, or the encoding in quantum double S3. In S3, you use the degenerate fusion space, like this degenerate fusion outcomes, to do encoding. So it's like this way. We have a two-dimensional plane, and we have 4D anyons. They are fused to 1G anion. And intermediately, we don't know how the leftmost 2D anion are fused and how the rightmost anions are fused. So there are some intermediate X and Y anions here. Then this form a degenerate intermediate charges, and they are unknown. They are in quantum superposition. So this can encode one logical qubit. I call that XY logical. And the three states, three admissible fusion outcomes will be AG, GA, and GG. Okay, so how to understand that in a physical system? Remember that we have a two-dimensional code. In this two-dimensional code, if we do not have any error, we will only have these anions, DD, and G. If you do a syndrome measurement, I call that M, you will only see 4D anions and 1G anion in your syndrome measurement result. And this is our logical state. Like the vacuum state in the toric code or surface code. We have this reference configuration, and these anions are called the reference anion. So our error correction is trying to always come back to this reference configuration without introducing any logical error. Okay, so right now you may ask me, what is like what's the form of error and how to avoid logical error, and what is logical error? So this is in this slide. You have this encoding into the reference configuration, and then it can be abstracted into this U model. Like you have a logical qubit composed of like 4D to 1G fusion chi, and have some intermediate state X and Y you don't know as a degeneracy. And why it is called U model? This was proposed by Cui and al. It is because they use this subspace of this fusion result to a U to encode a logical qubit. And the other result, they always discard that. But actually, you can check in their proposal, they can always keep ensure that by some adaptive protocol, there is no leakage into this space. So it is fine. You always have this qubit. Okay, so why we use this U model? Because in quantum double model, we can only measure anion charge. So this measurement of anion charge ensures that we can always do active error correction. Namely, we can suppress thermal noise. As a comparison, people may say, why don't we use Muchon's protocol in the very early days? Because in Muchon's encoding, they just use local degrees of freedom. And the local degrees of freedom cannot be measured using this quantum double model's measurements. So you cannot correct that against the thermal noise. Okay, so that's the reason. In this system, if we have this encoding in this reference configuration, how to do error correction? This is like errors will appear in the form as some pairs of anions, like C anions and E anions happen somewhere. And then if I do a syndrome measurement, I will see, other than those reference configuration, we will have some C anions here. We will have some E anions here. Then our decoder will tell us, you should fuse the nearby anions and come back to the original reference configuration. And if I do that, you see, here, we correct the C errors. That's good. But those E anions, they have a homologically non-trivial loop. Or sorry, no, I should not say like that. You have a non-trivial loop across these 2D anions, across the many reference anions. And this has a non-trivial intersection of their anion word lines. The intersection of anion word lines are logical operations, or you can say this E anion introduces some logical error. And this is something we want to avoid. So to get it slower, this is like we don't want to have some error, have some non-trivial anion a non-trivial word line intersection with more than one reference alias. So the key is that if you want to have some topological protection, you should always keep the reference alias far away from each other, and their distance will be similar to the concept of code distance in typical stabilizer codes. So here, the minimal distance between those d-anion and this g-anion will be the codistance of our encoding of this logical Q-cheat. So the key is the distance of those reference anions to introduce some topological protection against thermal noise. Yeah, and how to do that? Let me firstly introduce how to realize a universal quantum computation in this system and why it is not that easy to realize this fast separation between reference anions during this process. In the proposal by Cui et al., they show you have this logical encoding, and you can have a universal gate set in this fusion tree by these operations. The first one is braiding of d anions. You exchange the position of d anions in this two-dimensional plane. And this will give you this poly X, poly Z, and some Hadamard gates. The second one will be anion type measurement. Namely, you want to measure the total charge of two d anions, like these two rightmost d anions. You measure their total charge, and specifically, you need to determine you need to do two measurements. The first one is called MU. MU is like you want to project into the U space and this U perp subspace, preserving the coherence. So that's why I say they construct this protocol. They select a subspace to encode a logical Q-cheat, and then they always use this projection to ensure you do not have any leakage because you preserve the coherence. So when you go back, when you go into another space, you can always go back. This is the key in their construction. And also another measurement is called MA. This requires you to distinguish whether they have total charge A or G. If you look into the U space, you will see we want to distinguish one state from two other states. So this is like in a Q-cheat, we want to distinguish the 0 state and the other 2 states. And this is a typical way to introduce magic in Q-cheat computation. Then the third one is do a fusion space transition, because here we have all the single Q-cheat gates, and you need to have a fusion space transition from one logical Q-cheat into 2 logical Q-cheats and do some braiding to realize the C0 gate. So this set of gates will give you a universal gate set, and this is in their construction. But as I said before, you want to keep all of these reference anions far away from each other. And in their paper, they say that even though they have this encoding, they don't know how to actually introduce fault tolerance. Because, for example, if you want to do this measurement is very artificial. How can you have this kind of U measurement in anion system? And also distinguishing A or G is also very strange. So they say, okay, how this proposal can be made fault tolerant, they don't know. And in our paper, our contribution is that we actually make all of these operations, like with all these reference anions far separated with each other. So we can introduce this topological protection against thermal noise. Yeah, so this is what we are doing. So let me go into a little bit about the details in this paper. Yeah.
Yuan, we have a question.
Yeah, please.
So basically you're saying that this 2015 paper, like they said that you need to do a constant, like, do you need to do constant measurements or repeated measurements of anion type, like pi U and pi U?
Yes, this is like some measurement-based quantum computation.
Oh, I see. This is not syndrome traction. This is some. Oh, I see.
Yeah. This is we are in the these are the operation in the encoded logical Q-cheat. Yeah. So you are doing some operations, topological. Sorry, not topological operation. Actually, just operations on this encoded space. Right. Yeah.
And then, like, are you saying like you're avoiding Easton nu because you're doing measurements, or is Easton nu relevant here?
No. Because Easton nu just avoids the prohibits the transversal realization of all gates. But as you can see here, if we want to do a braiding of D anions, we actually requires a linear depth circuit, like lattice surgery. You move the anion around each other. So there is no transversal gate, actually.
Oh, I see, yeah, because I mean, there's a famous theorem that, you know, the circuit depth for moving non-abelian anions linear with the depth, right, so.
Yeah.
No, for every non-abelian.
S3, it's all with the group, so you can move the just like in.
So maybe someone will say for S3, you can do some constant depth realization, right?
Yeah.
Yeah, it is not fault tolerant. Actually, Suyan is here. Actually, we spent some time in checking. All of these proposals are not fault tolerant. Errors will propagate along this circuit from the head to the end. So how long you move the anion, you will introduce how large this error. This means that if you want to do a braiding, and then the error will also form a large loop, and then you will introduce a logical error immediately. Yeah, okay. So yeah, so let's move on. So as I said before, some people will say like you can do constant depth of moving anion, but actually this is not good because you will immediately make the error propagate constant depth. So how to do the first thing, how to braid these D anions to avoid this error propagate out of control. So our solution is that you move by fusion. Namely, our goal is to move this alpha anion on the right-hand side, one side to the right. So what we do is like we introduce a small pair of alpha anion and fuse the intermediate alpha pair into vacuum. A is the vacuum. Yeah. So if you successfully do that, you actually realize our goal. And we do that. When we do fusion, we need to do a syndrome measurement on the whole lattice. So every time we move anions, we'll simultaneously do error correction. So this is a way that you always like do lattice surgery. You want to move the puncture in the surface code. When you do that, you always do error correction continuously to ensure that errors can be corrected during this process. And then you may ask a question. If anions does not fuse into the desired result, what can we get? Because these alpha are from different pairs. So they will not definitely fuse to vacuum. And this requires some design of the protocols. We design the protocols to ensure that we can do some adaptive operation to ensure these alpha anions can be fused to vacuum definitely by several rounds with this probability converge exponentially close to 1. And N is the number of rounds we do this measurement, syndrome measurement. So having this moving by fusion protocol, you can always like just move and doing error correction, and you do braiding by keeping these D anions far away from each other, like this D anion far away from each other, so our distance is kept. So this introduces the topological protection in the first operation of this universal gate set. It is compatible with quantum error correction. Okay, so yeah, so I really thank the question because yeah, some people will say, okay, you can do constant depth, but this is only applicable for do quantum simulation, but not for quantum error correction. Yeah. Okay, so the second operation will be this anion type measurement. And let's remember that we need to do two measurements. The first one is called MU. You want to project into the U space and U perp subspace in this logical Q-chit. And also this MA, we want to distinguish whether the total charge of these D anions is A or not. Both of them are very tricky to be realized because the typical way of measuring charge of in the topological order is to fusion. You say, I can move this D anion together and do a local measurement, do a fusion to see their total charge. But you immediately realize that this will make the code distance become 0. So you immediately ruin the logical information encoded in this Q-chit. So we don't want to do that. We want to avoid fusion in doing this logical operation. How to do that in a potentially fault-tolerant way? So our solution is that we design a very smart like anion interferometry to realize those measurements. let me explain this using a animation. This is like we have this logical Q-chip, and then we want to measure the charge, and then we create a pair of Z anion in a very far distance away. Then I select one of these Z anion to braid that with this 2D anion. Like you braid this across this 2D anion, and then you fuse this 2Z anion back. You may produce a W anion here. This is the fusion result. And then you can use the smart design in this interferometry to read off this X anion by looking at this fusion result. This is very technical, and the details is in our paper. Like finally, by designing this interferometry, you realize this measurement using those remote measurement. You can read off X by this W. Yeah. So to go a little bit more into the details, for the first measurement, you want to measure this MA, the charge is A or not. You use Z anion equal to D. And then if you do this kind of calculation in anion theory, you will find that this W anion is A when X is A. W anion is G when X is G. This means that you can always distinguish A or G by directly looking at this W. Yeah. And also the second measurement is a very hard measurement projected into a subspace of this logical Q-chip U and U perp. You can also use Z equal to H anion and then do some braiding, and then you will finally realize this probability projection into this U and U perp subspace. We have checked all of that in our paper, and we have shown that all these local errors, namely the error do not create some non-trivial intersections with the word lines of two reference anions, will become global phases after the process, independent of X and Y. So it can always correct those local errors that do not grow too large. So this is the way to introduce topological protection in this process, this measurement process, avoiding any fusion. Okay, yeah, please.
So, so what's the realization of this braiding protocol on the hardware? Like, you're creating a pair of, so you already have a pair of, for example, D anions, right? Like you're trying to braid a W anion around like fusion outcome X. So what is like on the hardware, do you literally have to circle like one of the Z anions like around the pair?
Yeah.
You know?
I will introduce that in maybe 2 slides later. We have some experimental proposal.
Also, the accuracy goes exponentially to 1. Does that mean, after some rounds of synchrotron traction, is it that? What does the arrow actually mean?
Yeah, because here is a projective projection. Probability projection. Namely, you have some probability into this U and some probability you don't know whether it is in U and U perp. So that you have to do many times to ensure that we are very confident we are in U or we are in U perp.
So do you have to physically do this braiding a lot of times?
Yes, that's true. You have to physically do that for many times.
Okay.
Yeah. So for how those operations can be done in experiments, I will explain that in two pages later. Yeah.
We have another question.
Can you maybe you mentioned this and I missed it, but are these is this what double S3 realized in physical systems? I know there are some talks about it. Maybe in Continuum, can you remind us of who's done what with this double S3 theories?
Yes. So firstly, maybe there were some Nature paper by Continuum realizing this quantum double D4, right?
Right.
D4 realized.
Yeah.
And then they try to do some work on this Q-chip toric code.
D4 is not very.
It's not universal.
It's not universal. Right?
Not universal. Yeah. So for S3, right now we only have the proposal for this Q-chip toric code. It's also by Continuum. They realize a Q-chip toric, but not for S3. And for S3 right now, we do not have any realization in current quantum devices. And in that paper, we want to we want to show a fault tolerance proposal for this realization in these quantum devices, because some of the previous proposal, like for D4, for Q2 torical, they are not actually fault tolerant because they only do quantum simulation. They do not consider error correction process in this. And this is really
So they are not universal and not fault tolerant. I don't know what they are, but they're not, lot of nots, lot of shortcomings. So I understand the motivation, but so if you, so in your protocol, it looks like the promise is that you can do two essential things that these previous continuum papers actually failed, because they were not fault tolerant and they were not universal. So that's a great aspiration to have. But in that league of wanting to have these difficult things, there is also like Fibonacci-based proposal, which does do universal, but it's also hard to be fault tolerant. But when you, moreover, to do it is universal in the sense that you can braid and get non-Clifford gates, but to get an arbitrary gate is hard because you got to do a lot of braiding to get some arbitrary gate, right?
Yeah.
So you haven't shown us your proposal yet, but just looking at this slide, it does not look like manifesting these visions will be necessarily like short depth circuit.
Yeah. So this is
So practically, this is probably pretty challenging. Am I right?
yes, true. Because like for any this non-Abelian way, we actually non-Abelian realization, you always requires very low gate speed. Like you need to do a constant linear depth to do circuits to apply gates, logical gates. So it is somehow very, very slow. This is true.
Yeah.
Yeah.
Okay.
But the problem is that we have a proposal that can actually fulfill the original motivation of topological quantum computation, because the original motivation is that you want to have a code directly have a universal gate. Yeah.
Yes.
Yeah.
Okay, continue on, please.
Yeah. Thank you for the question. This is very good clarification because I did not point it out very clearly. Sorry. Yeah. So
Thank you for giving clarity on what continuum papers are not. Okay.
So yeah. So these are some details about these measurements, and this is the key construction in our paper to show, okay, you can have this way to become fault tolerant. So finally, we have two operations, braiding and alien type measurements. You can introduce some fault tolerance, and they are summarized in this picture. Okay, we have braiding, you have this interferometry measurements to infer the alien charge inside. And also, I claim that you can combine the first two operations in a smart way to finally realize this fusion space transition. And yes, they also have some topological protection inside. So I will not go into the detail about this step. So the conclusion is that if you have a good decoder, so this is I should clarify, because right now the decoding problem or error correction problem for non-Abelian is still an open question. Yeah. So, but the assumption is that if you have a good decoder for this topological code, you can realize fault tolerant universal quantum computation in 2 dimensions. So this is our contribution, and there is no magic state dissolution. So I believe this is exciting. And the next step is two questions. The first one is how to realize experiments, as I promised before, how to do quantum error correction. So this is the second slide behind the previous slide. And then we have this circularization of S3. Indeed. Yeah, please.
Sorry. Before you go on to the circularization, so can you remind me where, which part is the part that gives you universality? Because XZHC0 doesn't look like universal, so which is
this one, alien type measurement, 0 and 0 perp. Like this is a typical way in Qubit, because Qubit you have 3 states, right? And then you measure that into 0 and 0 perp. You can think about that this is a 0 perp is a qubit. So this mismatch of these two prime dimensions will introduce you some magic in this computation.
Thank you.
Yeah. Good point, good point. So yeah, so the circuit realization of S3. So these are some, indeed S3 is designed for realization in circuit actually. So they have some basic operations like this F operator. They are just some creation of pair of nearby anyons, and anyons are labeled by R and C. I use a different notation here. Just don't worry about that. This is just anion type. So you can have some ribbon operator creating a pair of local anyons, and then you can have this K operator like the syndrome measurement, measuring this plaquette and this vertex simultaneously to tell you what is the charge at this site. Okay, so these are the basic operations in the code. Similar to surface code, you have some string operator, you have some syndrome measurement. And then you can write down all of these circuits for these anion movements by just creating small pairs of anion and move this by fusion. The reason is very simple. S3 is a group can be decomposed into a semi-direct product between Z2 and Z3. So you can encode each edge into a Q-chip and a qubit. So that's the reason. And then by very carefully calculating all of these things, you can write down all of these circuits for this anion. And one example is this C anion. You can write down the circuit. It's not very difficult, composed of just some basic gates. And then also, you can also write down the circuit for syndrome extraction, this M. M is just composed of every size, this syndrome measurement. So you have a measurement on this two-dimensional plane, every side simultaneously. So I should emphasize that even though here I just say, okay, you can do this decomposition, writing down these circuits are really difficult. And I encourage you to check the paper to see there are some many designs in that circuit to make them become compatible with fusion and quantum error correction. But after having that, we observe that those circuits are very simple. And there is only one non-Clifford gate in the circuit. So here I should emphasize, the non-Clifford gate is in the physical level. So we should not say it is difficult. But why I say there is only one gate, because there are other gates are Clifford gates. They are just simple X gates, Z gates, and some CNOT gates. And these gates are well studied in current quantum devices. So what I mean is that only this one extra non-Clifford gate maybe have some difficulty in realizing that. So that's why I say it is very simple to be realized. Other gates are very simple, have been well studied. And it has low weight syndrome measurement circuits, just like this one. The weight is 8. So the conclusion, yeah, please.
Well, you can go ahead. Maybe after you finish the slide.
Okay, yeah. So the conclusion is that these circuits are really friendly to all quantum platforms. Like superconducting circuit, you require two-dimensional layout, and this code is two-dimensional. You require, for ion traps, you also require two-dimension, you also have this one. And for atoms, some people are studying these dual species like qubit and Q-chip, ytterbium, rubidium construction, and it can also realize this Q-chip and qubit realization. Yeah, so that's why I say, okay, it is very friendly to all of these platforms. So,
Okay,
yeah.
Question. The question is actually a few questions. So you said one non-Clifford gate in your entire circuit of I guess operation, but this is non-Clifford gate in the Z3 sense, right? Like for Q-chip sense.
It's a non-Clifford gate from qubit to Q-chip. Like the semi-direct product is like just some very strange algebra. Flip the Q-chip by this qubit. So this is a non-Clifford operation.
Yeah, there's a control charge conjugation, right?
Yes,
Like
exactly. This is control charge conjugation. So it's here.
Yeah.
This gate. I didn't say that explicitly. Yeah, it's true.
Yeah, I know it's control charge conjugation, but what I'm saying is it doesn't seem like on the physical level, it actually creates trouble for experimental devices, right? Because I mean, non-Clifford, like for example, single qubit control, like even for qubits, right? Like I want to realize a T gate, right? You just do a physical T gate, right? There isn't a big like resource cost, right? So
Yeah.
what's the advantage that you're trying to emphasize that I only use one non-Clifford gate? Like physically, why it's beneficial?
Yeah, I mean, just like all other gates are very familiar to those experimentalists. Only this control charge conjugation is new. That's what I mean.
So it's easy to program into a quantum software that for these people to implement. That's
Yeah. yeah, somehow like
Yeah.
this way too. Yeah, say.
Okay, good.
Yeah,
Thank you.
okay, thank you. Thank you. Yeah, maybe I should change that in the next version of this slide. Yeah. Okay. So yeah, so let's talk about active error correction. So in this code, the circuit level noise will be poly X, poly Z in qubits and qubit. For qubit, I use a hat here. Maybe you have observed that. And as an example, let me give you the intuition how to correct those errors. I think you already know that because this circuit level noise will be mapped to anyon errors, like poly X be mapped to this 2D anyon and 1C anyon. So the correction is like you move those anyon together and annihilate all of them back to vacuum. Okay, so but a question is that, can we always correct those circuit level noise by correcting anyon errors? In that paper, we present a proof. The answer is yes, because the anyon creation operators form a complete orthonormal basis. So from the fundamental theorem of error correction, you can correct error in one complete orthonormal basis. You can correct that in another basis. So you can always correct those poly errors by correcting these anyon errors. And that's why people only study like depolarizing noise or dephasing noise in typical quantum error correction. Okay. And then for anyon errors, we have this kind of scheme to do error correction. We identify them and we pair them up. And this is in preparation, collaborating with Suyuan. We want to investigate this very detailedly. But as I mentioned before, non-abelian anyons error correction is a hard problem. And the difficulties, as I summarize, are in these 4 aspects. The first one, you can have multi-anyon clusters. So there is no matching decoder in this system. What I mean, like if you have 2 Z errors on Q-chips, by measurement, you can create 3 C anyons in the system because C and C can fuse to C. Like this is called cyclic anyon. So you cannot do matching. Matching you must have even number of anyons in the system to do matching. This is the first difficulty. And the second one, the anyons fusion result is not determined before you fuse them. For example, if you see this 2C anyon, you don't know whether they will be fused into A, B, or C before you fuse these anyons. And the third one is noisy measurement. Actually, this is an open question in this field. Like there is no practical decoder to cope with noisy measurement because non-abelian anyons measurement is too complicated. And the current proposal, there is only one having a threshold 10 to the minus 4. And you don't want to use that because it's too low, not applicable. And the last one is a very practical problem, how to do classical simulation for this code. This code is universal. If you can simulate that in a classical computer, this means that you have the power to simulate the universal quantum system using a classical system. It seems very. So these are the 4 problems in doing this non-abelian anyon quantum error correction. And I will talk about the current progress in our work. Yeah.
Yeah, I think you missed a very critical word because you're describing the possibility of simulating a universal quantum computation circuit using like, I don't know, polytime classical resource, which will be, and you raised your hand and quote unquote something, and we missed this word.
Miss what? Sorry.
It froze for like 1 second.
You froze for 1 second. You're describing the.
I think.
Like, are you trying to say that it's kind of ridiculous that or like promising prospect or whatever that there will be a classical simulation for?
I mean,
so-
probably for sure.
So what I mean is that this classical simulation seems ridiculous, seems contradictory, but we have some way to do this simulation. I will explain the reason later. Yeah. Do I answer the question?
Yeah.
Yeah.
Also, for number 3, are you citing the paper by Poulon and Dauphiné? Is that the paper for noisy measurement that yours? Like
No,
10 to the minus 4.
No, in that paper, they only consider instantaneous error correction. This is for Ising anyon, right? For Ising anyon, but as I said before, anyons has movement like velocity, finite movement velocity. So their paper is not really physical. They study this phenomena. What I'm saying is the paper by Guanyu Zhu and Alexis Scotty, 2023 about this Fibonacci anions. They consider Fibonacci and they do a renormalization group decoder, and they finally numerically show that the error threshold is 10 to the minus 4.
I see. Okay.
So what I say is that we want to improve this threshold to relatively practical, 10 to the minus 2, 10 to the minus 3, something. We don't want to do RG decoder. If you use RG decoder, you will always have this kind of very low threshold. Yeah. Okay, so let's move on. For active error correction, so firstly, we describe our algorithm. Even though this is hard, you can still find some way to do error correction. For multi-anion cluster, you can find the union-find decoder. You can adapt from union-find decoder to do some error correction. So the idea is not that difficult. Like you have 3 C anions, you grow a cluster on each C, and then you merge the touching cluster together. And by setting some criterion for stop growing of this cluster, you finally identify these 3 C together and you move them together. So there are some details in the upcoming paper. So I will not describe that in details, but the way is like you always do this kind of growth and then setting some smart stopping criteria for this growth of this cluster and identify a set of cluster to do this fusion. And also for this undetermined fusion outcome, you do fusion aware decoder. What do I mean by fusion aware? This is called like you do multiple runs. For example, in this case, C anions are created by errors in this two C pairs. Our decoder will sometimes like tell us you should fuse this leftmost 2C and the rightmost 2C together. But if you fuse that, they will not go to vacuum because they are not from the same pair. So finally, you do that again. You just do that B fusion again. So you fuse again and come back to the vacuum. So fusion aware is a characteristic of non-abelian error correction. Namely, you do multiple rounds of fusion to see the result from the last round and then do decoding again to correct the error. Yeah. So combine them, we have proposed the fusion aware union-find decoder in our system, and we will like we are writing the paper and then we will show that the result. And also for this noisy measurement, we generalize that into this space-time clustering decoder, as we will also write it in this paper. So the last question is, we have those algorithms. How can you do this classical simulation? So let me give you the answer. How can you use a classical computer to simulate a universal code? Actually, this is solved in some previous papers to simulating the Fibonacci code. So we just adapt the method here to simulate the S3 code. So the key is that you don't simulate the code. You simulate the anion fusion trees dynamics. Let me explain this idea. Like, if we think about you have 2 Z errors, what actually happened in the system is that you create a pair of C anion by any Z errors. Like you have this fusion tree, a pair of C anion, a pair of C anion, and at the intersecting site, labeled by this purple circle, you fuse this C anion together into a C anion. So this is what happening. So to precisely capturing this fusion probability, you need to simulate this small fusion tree to simulate this anion. But it's fine, because if we do not have percolation, the error threshold is not that high. There are only small clusters of fusion tree in the space. Namely, this is the figure. Globally, you have this small fusion tree populated in a very distant, far away from each other, so the size does not grow too much. And you don't need to worry about the system to become like, you only simulate a small part of this fusion tree, don't need to worry about this large dimension. More precisely, from percolation theory, every cluster only contains n proportional to log L. L is the system size, anions. You only have this log L anions. Even though the dimension of the fusion tree is exponentially to n to the number of anion, it's fine. The total complexity is still poly L. So that's it. So you can still do this simulation. Yeah, and then let me show you some result. This is our current result. You can sample those anions in the system, creating some pairs, and some of them can be fused immediately. Some of them will need to be fused in the later round, because right now we correct that we cannot like completely fuse all of them, but we identified into the cluster. After one round of error correction, some of them are corrected. And our fusion aware decoder will tell us, okay, there are some residual anions. We need to move them together and correct again. So we have this cluster, and finally, this cluster they can be correct in one step. So this is the process of doing anion error correction. We do this coding to write this code. It spends almost a whole year, and thanks to Suyuan. Suyuan is the one who majorly write this code. And then we will post another paper. This is called ASIM. Why we call this ASIM? Because it's an anion simulator, error correction simulator. And this is like in parallel to the STIM, the package for this stabilizer simulation in the stabilizer code. So we hope that in the future, everyone who is doing anion error correction can use our package to do this simulation and finally to see, okay, we have some threshold numerically and it's practical. Yeah. So these are all the progress in our current efforts in realizing a topological quantum computer. So let me give you a brief summary and outlook for today's talk. We have this code, interferometry and braiding, and we believe that S3 is the one to be the optimal choice for topological quantum computation to simultaneously realize quantum error correction, universal quantum computation, and has some experimental feasibility. And we show a photon universal dataset in the system. We show that it can be realized in circuits, and then we have some progress in active error correction for this system. So we believe this is a solid step to our practical topological quantum computer. And in the future, there are many, many different directions we can think about, like this continuous error correction. We can finish that. And also the resource estimation to compare whether it is good or not compared to surface code, color code, or other current codes. And you can also think about mapping it into some statistical physics model to consider its optimal decoder and also the LDPC construction in this code to have universality and LDPC. So I believe doing these steps will make this proposal a practical protocol for large-scale quantum computation compared to the current proposals. Yeah, thank you very much. These are all I prepared today.
Thank you so much for the talk. Any questions?
I have a question. I think maybe I missed it, but I didn't see, like, so, I mean, we happily, criticized Quantinuum, but, we should give them credit that they actually work with physical systems. So when they say realization, however unimportant things that they realized something. How can we realize this S3, double S3? It's not like people didn't know double S3 would be interesting to do. I think people haven't yet figured out how to put it on a physical system. Maybe just not yet. But do you have an idea on which physical system can one how realize this ES3?
I believe superconducting circuit is the best one.
But you have not sketched for us what would be a strategy in this talk, right?
Oops. I think, okay, you should be good.
Yeah.
All right.
I didn't hear that, sorry.
You have not sketched how can one implement ES3, realize it on a physical system.
Oh, yeah. I did not actually come up with a compilation or something like that, because maybe this will require some other efforts from some experts more in this field. I am not an expert in doing this compilation, but I actually believe superconducting circuit will be the best, because in that system, the transmon qubit is not that difficult compared to the qubit, right? And then you can have those gates easily.
Okay.
I have a question. So you mentioned this LDPC non-abelian code, because from my understanding, there are multiple different ways that non-abelian quantum level can be used in universal computation, right? Like this U model is one of these proposals, right? And you also have other proposals, for example, like this sliding whatever approach that just you have this non-abelian quantum level, but only at the intermediate time step, right? It's kind of another proposal. So in the case of this U model, right, how do you scale up like your protocol? Because based on my understanding is that you need a huge patch of quantum double S3, right? And you need to create a lot of these U trees.
Yes.
Right, and so my question is, how dense can these U trees be, right? Or if you engineer, for example, the topology of a base manifold, is there a prospect of, you know, a very high coding rate kind of quantum WS3 quantum computer, like based on U model?
Oh, I don't know. So sorry. So first is that I don't know, because this is a really a deep question, not that easy. Like you directly generalize that from U model to some like something, because if you want to realize, if I can understand that correctly, you mentioned that how can you promote that into LDPC, right?
Right.
Yeah, and if you want to do that, you firstly need to identify a topological quantum field theory for this LDPC. So it's not direct. I don't know the answer right now, because it requires some complicated construction, not that easy. Like you change the stabilizer and then something, and then you have this one. It's not
So, I mean, there are multiple ways, for example, when people go from like surface codes to, you know, bicycle codes, or going from, for example, color codes to like these homology, whatever code, like, so there are different strategies, right? First strategy is you modify the stabilizer, right? You go from surface code to, say, bicycle codes, right? But there's another strategy, which is, you know, going from color code to just a color code itself, but on a very complicated manifold. Right, so that will also give you, you know, tons of logical qubits, because the topology of the underlying manifold is extremely interesting.
I see.
I think there are similar questions that can be asked probably for quantum WS3, but I think you have another degrees of freedom that you can play with, which is, you know, if you further expand your U model, if the U model itself can be extended to you know, encode more information, like if you allow more fusion procedures on your U tree, will it be able to encode more information? Or maybe you want your U model to actually live on a very, you know, topologically interesting manifold, then this maybe one single tree will already have a lot of, you know, computation power or whatever. Like, you know, I don't know whether people have considered these aspects of scaling up or not.
I don't know. So maybe we can work on that. We can discuss that later. Yeah, I think like
Okay, sorry.
yeah, S3 is something that people don't care about it. I don't know why. I always to talk to people like this S3 is interesting, and they say it's too complicated, so it's not that interesting to me. So yeah.
I think that complicated has to do with, you know, what's close to reality. I was just talking to a computer scientist and said we're going to work on materials, and he didn't realize materials mean something made of atoms and have connection to periodic table, right?
Yeah.
So for some people, their mission and vision is to hold something in their hand. And for them, what's going to be closest to being able to held in their hand is more interesting.
Yeah.
It's very subjective, in other words.
So last month I go to QEC 25, and then I explained to some computer scientists what is this protocol. And the first question they asked me, what is a particle? So I say Enya is a particle.
My experience, yeah. They've forgotten that they're made of atoms. Thank you very much. It was very interesting.
Yeah, thank you.
Thank you so much.
Yeah. So what else should I do?
Nothing else. I guess that's it. Thank you for contributing to our last quantum theory seminar. We appreciate it. We're looking forward to seeing that paper out, the one that is in preparation.
Okay, thank you very much.
All right.
Right.
All right. See you. Have a great rest of the day.